Okay, so today is I believe it's 2.3.1, and I will not go look at the worksheet yet. I want you right now in the notes so that we can just do some practice problems together. First of all, I need to review some graphing with you because you're going to be tested on graphing here in not too long. About a week from now, this comes the graphing test. So I hope you know what that could be, and I want you to give me three options. What I mean is, let's say that this was x squared. Then it would also be the same as x to the fourth and x to the sixth, like this. But it's not like x squared. What is it like? And then name two others that would look a lot like it. Those are it. Yes, 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 but there's two others that are kind of like it. Good. Yep, yep. Okay, everybody's getting them right. X to the third, x to the fifth, and then weirdly, some people jump to x to the ninth, which is true, but x to the seventh would be the next logical odd number. Anyway, okay. So those are the odd ones. I hope you remember that the even ones would pretty much all look like x squared then, right? So y equals x squared or x to the fourth is almost indistinguishable between the two. Depends on how you set your window, but you can set your window such that you can't even tell the difference. If you graph just the x to the fourth on the screen, it looks just like you had graphed an x. Okay, I think you get the idea there. What are the ones that look like this? I call it a volcano graph. Now, to get these straight in your mind, you better get the two that are like each other. There's this kind, and then the other kind that's a lot like that looks like this. Y equals x to the something. All right, I know many people have forgotten. I'm going to not keep you in your misery for that long. I don't want you to put it as 1 over, but you could think of it that way. Here, what I mean is 1 over x, actually, that's not even right at all for this one. 1 over x would be kind of right for this one. Do you remember that? That's 1 over x? But that's really like 1 over x to the 1, right? And that's really like y equals x to the negative 1, right? So if that's x to the negative 1, then what are the others that are going to be like it? Negative 3, negative 5. Yeah. So this family is y equals x to the negative 1 and x to the negative third, x to the negative fifth, etc. So then what does that leave for the mountain of a volcano kind? What do you think? It's really not that complicated. Negative 2, negative 4, negative 6. Okay. There is a way to remember it. They're all negative. Okay, so it's just a matter of odd versus even, right? Does this look more odd? This does. To me, this seems more like an even thing. How about this? Does it have even symmetry? Remember that? Okay. And this one has odd symmetry. Remember that? Where like a point here would go through, touch that, and then touch something on the other side. Okay, this one has even symmetry, like a point here would be reflected straight across to a point over there. Shouldn't be that far away. I should probably move it over a little bit. But anyway, I think you're getting the point. This one's even, got even symmetry, right? If you can get more ways you can make connections in math, like oh yeah, even that symmetry thing, odd symmetry thing. The more connections you can make, the better. All right. Yes, ma'am. Sure. This guy? Okay, yep. Yes, but you won't see them that way. But it's good to know that that's the same as this. And this is the same as that. Make sense? It's good that you know that. but I think you're going to see them this way more commonly. Okay, but it's good to know it. All right, so what's the last kind? Give me one that is a different kind of graph that I told you about the other day, but I haven't mentioned yet. X to the something. Yes, square root. 1/2 power, or 1/4 power, or 1/6 power. As opposed to the other family, it's like the Hatfields and the McCoys. X to the 1/3, or X to the 1/5, or X to the 1/7. They're going to be different, right? So what do these green ones look like? Do you remember? Well, you know what the square root graph looks like, don't you? There we go. So X to the 1/4 would look a lot like X to the 1/2. X to the 1/6 would look a lot like X to the 1/2. Okay? And these, the ones that have odd fractional powers, or the denominator's odd anyway, would look more like, well, it's a lot like the even one, actually. It starts the same way, but it continues. Continues. That's odd. However you want to remember that. So the family here is X to the 1/3, or X to the 1/5, or X to the 1/7, etc. This is X to the 1/2, or to the 1/4, 1/6, etc. Get that door for us, please. Thank you very much. All right, so there's a whole bunch of kinds of fraction, sorry, not just fraction graphs, but a lot of different graphs that you're expected to know on your next test. Now, are you also going to be expected to know what happens if we, like, move it over and stuff? Oh, yes, you are. So, for instance, let's say we have y equals x to the 1/3, except it's been shifted +5. Well, that shouldn't be that hard for you. First of all, this one would be a pretty easy one. It's an R2 level. You'd be expected to know, okay, that's the parent one, right? And I only did one thing to it. So this is definitely an R2 chemical. So where am I moving it? But there we go. Done. It's a sketch, not a full graph. If it was a full graph, you'd use an X lecture. Yes. Good question. If it's a graphing test, then they have the option of asking you for a sketch or a full-out graph. If you say graph, then you whip out the XY chart. You make sure you pick numbers that work nice. Like, for instance, what can you take 1 to the 1/3 power of really easily? Yeah, what you're asking is the cube root of the thing. Cube root of 9 isn't quite so easy. 8. 8 works well, so I pick 8. 8 to the 1/3 power is 2. 2 plus 5 is 7. 8 comma 7 is on your graph. Get the idea? And then I pick other things like 0. I can put 0 to the any power really easy. It's 0. And then 0 to the something is 0 plus 5 is 5. 0 comma 5. And then 1 works pretty well. Cube root of 1 is 1. So put in a 1. Cube root of 1 is this. Is 1. 1 plus 5 is 6. So anyway, if you needed exact points, all you got to do is throw in an XY chart. Otherwise, generally, do you get that this graph has just been moved up? Okay. Now, what makes it move left or right? The way here makes it move left or right. So if I make it like -2, now I move where? Right 2. Now it's kind of hard to tell when you move the graph right 2, but there we go. Let's do right 2. Okay, so that covers a lot of the stuff on the front page of your homework for today. The next, and that also stuff that you weren't even asked about, like you're going to be tested on, but it's not on your worksheet. You're just reviewing graphing. So now we're kind of all caught up. So what do you need to know next? Next, you need to be able to look at a graph like this. I can tell you this graph has got an x to the 3rd, or an x to the 5th, or an x to the 7th. Just because the ends go in opposite directions. One's up, the other one's down. If they're going opposite directions, then you've got something that is odd on your hand. Okay, so this is the equation for something like that. That's an example of a possible answer. X to the 3rd plus 2x. All right, I'm going to show you another one. I'm going to give you the equation this time. All right. You ever heard of flyover country? People rip on the Midwest. The United States got this big inner middle part, right? That's the Midwest, and people will, especially that live on the coast, will describe our area as flyover country, and as in they fly over it when they're on their way to someplace. So anyway, you can feel offended later. This is flyover country because it doesn't make much difference at all on my graph. What really makes all the difference is on the coasts. That and that. That makes a big difference in my graph. Would you agree that that one right there is called something special? Do you remember what it's called? The Y-intercept. So the Y-intercept is 1. That is something huge you can identify on a graph. Like if you're trying to pick out, is this graph possibly right for that equation? And you could say, nope, can't be it. It's supposed to have a Y-intercept of 1. This doesn't have a Y-intercept of 1. It's got a Y-intercept of -1. Okay? How many questions are that simple to? As long as you can catch that. Oh, it does look kind of like an odd one because both ends are going opposite directions. That's a good thing. They had that part right. One's going up, one's going down. So for an odd degree, it's supposed to be like that. But the Y-intercept is wrong. All right, tell me. Could this graph possibly be right for the function that I just did? No. Because what? It's not this 4 at the end. That's not what's messing it up because it's going through what could be positive 4 right there. What is messing it up? Yes? It's supposed to be even. It says an even number here. The biggest degree is even. Its degree of this function, which is the biggest one, is even. And that's supposed to mean that they're both supposed to go the same directions. This one's going up, this one's going down. That makes this one an odd one, this that I graphed here. Can't spell down. O-W-N, June. All right, I give up. Down. Okay. So, actually, I'm going to say, I hope you're saying to yourself, that can't possibly be right. There's multiple reasons why it can't possibly be right. Give me one of them. Yes, sir. And this would indicate the what? What's that thing called? The Y-intercept. So this whole graph right here should not be touching up there in the positive territory. It should be touching down here. Okay, good. That's one reason for sure. Do you remember what these guys look like? The x to the third kind? Ring a bell? Doesn't it all look right, does it? Okay. All right, so that's definitely out because that negative exponent would throw it off. Okay, but even if I change that to a positive 3, it's still going to be messed up because of the Y-intercept thing. So what if I change this to like a positive 4? Now, could this be possibly a correct graph? Because it's odd, meaning one's going up, one's going down, and it's got a lead, not a lead coefficient, sorry, the number at the end, the Y-intercept, is approximately right. Okay, how many of you feel like you get that whole n thing, n's up and down thing? You get that? All right, good. Then here's the last one then. Let's talk about this. 4x to the 4th minus 2, okay? You get this, it says minus 2 here, so that's the Y-intercept, so it has to go through this. Okay? Now, could this possibly... You're right. Now, they're both going the same way. That goes with even, so we're good there. This is the Y-intercept, it's supposed to be -2, so we're good there. There's one more thing that I haven't taught you yet. Need a negative in the front. Very good. Now, how would you be able to tell? This is the last piece of the puzzle for today. If there is a negative in front, pay attention. This is important. If there is a negative in front, it does not tell you that both sides go down. It actually only tells you that the right side goes down. The other side will follow it based on the fact that it's even and they have to both go the same direction. If we assume that this means that both sides are down when you have a negative in front, then you'd never be able to do an odd one. Because remember how the odd ones go opposite directions? You can't have both sides going down, an odd one. So as soon as I did this, you'd be like, well, both sides have to be going down. Well, both of them are going down, and it's odd. That's impossible. If it's an odd-degreed function, if one has to be up, one has to be down. So if the lead coefficient just tells you the right side here is down because it's negative in front. So if the right side is down, then now I can logically choose, okay, and since this is odd, they have to be going opposite directions, so this side must be going up. And then I just have to go through this spot and I'll have it. Positive 2, that's like here. So now I can make this almost any way I want to. Actually, that one wouldn't pass the vertical line test, so I better fix that. There you go. There's a graph that could possibly be. Notice, is this exactly right? No. And it's not that important for you to have exactly what they look like yet. But if I pop a graph up there, I want you to be able to go, okay, I know that one's even. You get why it's even? Both ends are going down. Is the lead coefficient negative or positive? Negative. So it must be something like negative x to the something even. I'm not going to say squared either because it's got that extra loop in there. So I'm going to say x to the fourth. What I mean, because it's not a parabola. If I said x squared, I'd be implying it's a parabola. Something bigger than degree 2 then. And then the last thing, I don't know, flyover country doesn't really tell me much. The last thing I know is that it goes through a pretty high, like maybe like 8, so I'm going to say plus 8 at the end. It must have a y-intercept like plus 8. Okay, last thought is I want you to actually graph this one. Go ahead and type in negative, we use the negative key, not the minus key. Negative x to the fourth plus 8. We'll see what it actually looks like. Remember, we were saying that we don't know exactly what this thing looks like, but we know that the right end has to be going down. And the left end has to also be going down. And we know it has to have a y-intercept of 8. So as long as it has that, we'll be good. I'll pause for a second, put up the calculator. Okay, so I put it in my calculator, and there it is. Remember me saying that those x to the fourths kind of look like parabolas? And then the negative makes it flipped, right? Now what's that plus 8 do? Moves it up 8. That makes sense from that perspective? All right, also from this perspective, do you get that both ends are going down and that works for an even function? And then from this perspective, it's got a negative in the front. What's that supposed to be telling me, the right or the left? The right side is going down, and it works from that perspective. And then this plus 8 is also the what? Y-intercept. And the y-intercept is 8, so yay. It looks like it worked. Well, it should be. It's a calculator. It's usually pretty smart. So, all right. So now, what would you be asked to do on this problem? Just a few things. First of all, know that ahead of time, it better be going both of them heading down, otherwise something's wrong. Because there was a negative in front, but the right side was down, and this meant that they both had to be doing the same thing. Both ends going down together. And the other thing is, they're going to ask you to find the extrema. The extrema are not the ends. That's called end value. Like this end's going down, that end's going down. Extrema are the high and low spots, like that spot. That's a high spot. Remember those? Maxes and mins, local maxes, local mins. Do you remember talking about that? If those, all the local maxes and mins together are called the extrema, extreme spots. They're not going to ask you for how low did it go, because it's going to go forever. It's going to go to negative infinity and negative infinity. So it's going to ask you for the extrema, which is the local mins and maxes, so like there. So let's remind you how to get those. And also it's going to ask you for these spots. Those are called the roots, the zeros, the x-intercepts. But your calculator only knows them as one thing. Zero. I'll prove it to you. If you look on the second calculate menu, everybody hit second, calculate. Do you see x-intercept anywhere in there? Do you see roots anywhere in there? You see solutions anywhere in there? No, but you do see zeros. These all have there's four names for this, but the calculator only uses that one. It never says roots. It never says x-intercepts. It never says solutions. But it does say zeros. You got to know all those words, because on the test they might say, what are the x-intercepts? And you'd be like, oh, that means zero. What are the roots? Okay, so let's find the zero on this. Everybody do it with me. Go to second calculate, zero. And now, we have to be to the left of our zero spot. So I'm going to go to this zero. I know there's two of them. Please go to the one on the left. And I want to be to the left of it, which is actually underneath it then. And I hit enter. And for me, it puts in a neat old little dotted line to the left of the zero. Yours, it probably doesn't. It probably puts in a little triangle. But then you hit enter when you're to the right of it, and now I got two triangles. It says it's between here and here. And now I go right on top of it, and I hit enter, and it tells me exact spot is negative 1.62. That is the x-intercept, or the root. They're going to ask you for those on the homework today. All right, everybody go do the right-hand side one all by yourself. Second, calculate the zero. And then I'm going to ask you to show it to somebody near you. I'll tell you who in a second. You guys are going to go diagonal. Okay? You guys are going to go straight across. You three are going to compare. You two are going to compare. Let's see. You guys are going to go diagonal, 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 diagonal. You're going to compare across the pig. And then you two are going to compare. And you two are going to compare. And then true, you turn around and compare with her. All right, show them that you got the right-hand side one. If you don't, that means you maybe don't know how to do it. You need to know this skill. Super important. Pausing for a second. So no. Okay, we checked to make sure everybody knew how to do that. Now let's go find the maximum on this stuff. Second, calculate the maximum. Left bound, that means get to the left of it. Enter. Right bound, get to the right of it. Enter. Yes, get on top of it. Enter. Please compare with the other person that I paired you with. I know it says some weird number, like negative 5. That means that it's trying to say it's rounding to 0. 0, 8. Make sure theirs says the same as yours. Otherwise, maybe you don't know how to find the maximum. Pause for a second. Your first number might be slightly different than theirs, but as long as it rounds to 0, then you're fine. Okay, just to clarify, I understand that your first number is probably different than theirs, because the calculator can't just say 0. I really wish it could. Actually, it can. In weird cases, it does. Does anybody's calculator say 0? One person's got 0. Two people got it to 0. Okay, now if it's not 0, it's some decimal like negative 3, but then to the negative 5 power. That means like 0.00003, and that's pretty much 0. So I know these numbers are different than each other. That doesn't matter that much. As long as you get that that means 0, and that's an important point for you all to get. Don't come up to me on the test and say, well, I wrote this because I thought that's what it meant. What it means is 0. This is rounding to 0. All right. I wish the calculator could just say that. Maybe on newer, different kinds of calculators, they're smart enough to figure out that that's 0. All right. One more, and if you can find, actually, you know what? Let's just do the first problem of this kind on the homework. So everybody find the homework for today. I'll pause for a second. We'll fill that up. Go. All right, so we've got the worksheet up now, and it's 2.3.1. There it is, 2.3, number 1. The first few are ridiculously easy. They are just make a quick sketch of it. And if you remember what x cubed looks like, both of these are x cubed, basically. That's been moved a little bit. That's moved 1 to the left, up 2, been shrunk a little bit, which on a sketch you'll never be able to tell anyway, so don't stress about it. You definitely would notice the flip, though. A flip on a sketch you can definitely notice. So this one, for example, if you want to sketch this with me, number 2, I'm going to start with the x cubed graph, which kind of looks like this, and then I'm just going to move them around and stuff. 1 to the left, up 2. Then I'm supposed to stretch it, which, like I told you, you really can't even tell it's been stretched. And then I'm supposed to do a flip. I really would rather have flipped it back here. It's so much easier to flip back here. So I'm going to do my flip back here. That's one of those times when it's useful to know that I can do it from outside in if I want to. So I'm going to go outside in, actually. So on the outside, I have a stretch. Then I'm going to move it. The stretch, like I said, wouldn't matter much. I already got my flip done. So now this one's out of here, and now I have this one left that's been flipped. And then I'm going to move it 2 up, and I'm going to move it 1 to the left, and that's pretty much it. And then I would have to list the things that I did. First thing, transformation. First thing I did on the outside was a vertical reflect. The second thing I did was the stretch, vertical shrink, actually. I know I cheated, but you can't even tell what you stretch the thing if you stretch a sketch. So for a Dr. Seuss book, stretch a sketch. And then number 3 was this thing, up 2. Number 4, I went to the inside and went left 1. Yep. What? Your question? So don't what? Oh, it does depend. This is the first time I can even remember when my life was actually better working from the outside in. But it was just because I had got that in a weird spot, and now I had to flip it, and I was like, what in the heck is it going to look like when I flip it? So I decided to go from the outside in. Depends on the problem. Okay, clear this. And now I'm going to go to this kind. Graph the polynomial on the graphing calculator. That says them offline, that's fine, but I got to be able to read, stupid computer. Okay, sketch it, identify its extrema and zeros, and explain how it is related to the monomials from which it is built. Okay, it's pretty easy when you can graph it on your calculator and then sketch it. So for Pete's sakes, you're just copying what's on your calculator screen. That's not hard. Then, identify its extrema. That's like the maximum. So I can calculate maximum. Or so I can calculate minimum. That's also pretty easy with a calculator. This last part, the only thing that threw me, explain how it is related to the monomials from which it is built. Okay, here's that's the flyover country part. Remember what I was talking about there? Do you get how this one affects it? This one really doesn't affect it at all. It's pretty much that graph of 2x, or x to the 4th. And this part doesn't affect it much at all. That part affects it. So if you look underneath the graph, you'll see where it's sort of trying to hint that, okay, how is it related to this? How is it related to that? Well, it's not related to that at all, because that's not the lead coefficient. Only the coasts. The beginning and the end of the equation actually matter. So how is it related to that? Well, and x to the 4th, you know that kind of looks like this in the graph, right? So it kind of looks like that when you're done with the graph. That's how it's related to it. It pretty much looks like this. This doesn't have much effect on it. So that's all they're really trying to get at in these questions. It's like, which one seems to affect it? The one in the front affects it. The other one doesn't. So again, on this one is one it pretty much looks like. That's flyover country. Doesn't really matter. The end of the number plus 0 means it hits at 0. It means it has a Y-intercept of 0. Okay, and then let's move to the very end of that worksheet, and there's one last thing that I need to teach you here. This will be easy because, like, especially, what is this part again? Y-intercept. Do you get that the Y-intercept is 104, so I can go look at these graphs and just figure out which one has a Y-intercept of 104? And I can rule out most of them just based on that. Okay, then the other thing is, the lead coefficient here is positive. You remember how that tells me that the right-hand side is going up? Since the lead coefficient is positive. So I know that the right is up, and I know that the y-intercept is 104, and that means there can only be one graph that could possibly be it. All right, so this section 6, 7, 8, and 9 should be easy peasy for you. And then let's take a guided tour here of this last one. Describe the end behavior of a polynomial using limit notation. All right. I think I'm actually going to push, I'm going to say a quick example here for people that are, whose teachers are covering this today, but I'm going to mainly teach you this tomorrow. But I can watch quickly how this is done. All right. I'll give my longer explanation tomorrow on how to do with limit notation. All right, so basically negative x to the third means, first of all, x to the third looks like this, right? And negative x to the third is flipped. So it's going to look more like this. Then it's got a y-intercept of 3, so that means it's got to be like up a little bit. So basically it sort of looks like that. There's my sketch. Now, how do I say the end behavior with limit notation? That's the only part I'm saying you'll probably learn more tomorrow than today. And this left end is the left end, and it's up. This is the right end, and it's down. The way to write that with limit notation is this. The limit of this function as x approaches infinity. I should actually put that, oh, right, should put that x approaches infinity over here, that is the right end limit, and I just haven't said what it is yet. Why is it the right end? Because as x approaches infinity, I'm going that way. This is where the x's are getting bigger and bigger, right? So it's just saying as you move that way on the graph, what's the limit of the graph? As I move this way on the graph, what's the highest or lowest it ever gets? Because I already know the x is going to infinity. So I know x. What I don't know is y. I put the y answer right here. The limits are always y values. And as I move way to the right, this guy gets lower and lower and lower. If I move infinity to the right, do you get that it's going to end up way, way, way down there? So its answer is negative infinity. That was the right end limit because I was going way over here as x approached infinity. All right, watch me change it to the left end. The only thing that's different here is x will be approaching negative infinity. That means I'm going way, way, way to the left here. And as I move way, way, way to the left, the question is, what's the y value right there? How high will it be? When I move infinity to the left, it'll be infinity up, which is positive. I know you probably didn't process all of that yet, but that was the left end limit on this function. I will teach you that more thoroughly tomorrow. That is something you will be tested on, writing limits. This is just, I'm considering this just a little taste of it, a little foreshadowing of the lesson I'm going to give you tomorrow on how to write limits. But for anybody who has to do it from this video today, I wanted to at least throw it in there for those that need on today's video. Another video tomorrow on this.